This is a video I had no intention of making, but I started looking at some data and playing around with the data, and I thought this would be a good exercise for my physics students to model data that's not necessarily physics related. It's the virus related COVID-19 virus data, but it's modeling nonetheless, and I thought it would be good practice. And the more I looked into it, the more I thought it might be beneficial to a wide range of disciplines. So just wanted to call your attention to this website here. The Center for Systems Science and Engineering at Johns Hopkins University is a place where lots of people are getting data, and this was sent to me by one of my administrators at my school as something to look at. And I thought this was, a great, beautiful website with some very interesting data, and I just wanted to look at this data here. And you can see that this is not exactly exponential. This data here at the end kind of looks like it could be exponential. There's a lot of structure here that comes because of how the governments are changing, how people's attitudes are changing toward the virus. But this last bit of data here, it's certainly data, this was March the 12th or so up to March 26th, is data that the world understands what the virus is doing, and I thought it would be neat to model that. Obviously, it's ramping up. These are the cases worldwide, and I'll just show you what model I've built here. And basically, what you're doing is you're taking the data from the 12th until the 26th, which is the white data here. And that is fed into a graph, and then we grab the coefficients, the model coefficients, exponential growth model coefficients here, and then we can model the future in these orange boxes here. And just a few disclaimers here. I am not an epidemiologist. I'm not a biologist. I'm a physicist, and number one. Number two is these are cases worldwide, not fatalities worldwide. And number three, and this is perhaps the most important, is that the model that I've written is one that I wrote in just a few minutes, and I'm going to walk you through if you want to model it yourself. But it is modeled on the current data. It does not take into account changes in behavior or changes in medicine or changes in treatment or changes in government action or anything like that. But I just thought it was interesting because I don't think people understand really what exponential growth is like. But these are the cases here worldwide. This is the current population of the globe a few minutes ago. And if you look at it, it's only 0.02% of the current population on the 12th, and then 2 days ago it's 0.07% of the population. So you look at this and you think, oh, it's probably not going to be affecting me. And so if people go about their daily lives, let me just show you what happens if you continue business as usual. So we can continue to model this down, and this over here, this column here, is the percent of people on the planet that currently have the virus. So it's still less than 1%, less than, if we model it here around April 21st, which seems like a long time from now, 1% of the people on the planet will get it. Again, if we continue to behave like we behave, or like we're currently doing, then that's the case. And then on 5/13, 10% of the population will get it, and then by June 5th, 100% of the people on the planet will be infected by it. Now, obviously, that's hopefully not going to happen. Hopefully, we get, we change our habits and things like that. We won't be affected to that extent. But I just wanted to show you what the current numbers look like, and really what this is an exercise in how to model data. All right, so if we put the old model aside, let me show you as fast as I can how to model the new data. So again, I'm getting the data from Johns Hopkins CSSE data, and basically what I did is I just come over here. So I've got my little Excel sheet on the side. I'm going to hover over this data here, and on the 26th, well, let's start here on the 12th. Gotta get my act together here. Apologize. So on the 12th, there's 145.2 thousand cases. Okay, so I come over here and I write 3-12, 20, 140, what did I say it was? 145.2, 145.2, sorry. Don't know what I'm doing. So that's the number of cases worldwide, and this day number would be, let's just call that day number 1. That's when we're going to start to model the data. Okay. To continue this, we can just simply click on the date, drag it down, and that adds a day to all of our dates. This date here, we can say equals the day above plus 1, and that becomes 2. We can copy that down. And then the cases worldwide, we would just hover over the 13th and write 156.1. And do the same thing for the 14th, 167.5. That's 167.5 thousand people. And we could just continue to hover our mouse over this data and continue to fill in. I'm going to do that now and pause the video. So I've entered the data you see here. I want to copy these two cells, drag them down so we have the date and the day number also continued on. And then let's add in here what the current population is. This is just to see how widespread the virus is relative to the current numbers. So what we can do is we can pop over to the world population online and just enter that number here. Let's just call it 980 because it's about to be, is that right? 980, yeah. Okay, and we can just copy that number on down. By grabbing the corner, and if we highlight, we can turn it into a comma separated number. So is that right here? Yeah, okay. And we can calculate what that number of cases worldwide is as a percentage of the current population. That's easy. It's just the cases divided by the current population. It's a very small number. We can turn that into a percentage and then increase that decimal so we can see that structure. Any equation my students know I like to turn yellow to alert us that, hey, that's an equation. We can drag it down. So it looks like that, you know, on the 12th, it was only 0.002% of the population, which is not great, which is not, you know, a big number. And then a couple days ago on the 26th, we see it's 0.007 or 0.008%. Still numbers that most people are not concerned about. Let's take our data and graph it now so that we can do some modeling with it. Just going to make a scatter graph. Okay. Select the data. This is the proper way of adding data to a graph. We're going to choose the X values, which is going to be the day number. How many days since the 12th of March. And then we select the Y values, which are our cases worldwide. Again, let me reiterate, these are cases, not deaths. Say OK, say OK. And you can see that that curve is nice and looks like it could be exponential. We'll see that in a second. And of course, we need chart titles here and axis titles. So you press the little plus sign there, choose axis titles. I'm going to pause the video now and enter my chart title and my axis title. So we have our axis and our chart titles entered, and the number of cases I'm going to call N, capital N. We can stretch that out a bit. And then the day number I call D. Right, just to be clear there. All right, and to clean some things up, maybe we highlight here, we turn into some borders, and we make all the data centered. Okay, so let's fit a curve to this data and see what kind of curve fit we get out of it. So add a trend line, more options. I think it's going to be exponential eventually. It may not be a perfect exponential fit right there. You might want to model it polynomial, which you can certainly do, but I'm going to go ahead and model exponential because I think that's what data is going to show eventually. And then we're going to display the equation and also the r-squared value on the chart. The r-squared value simply tells us if our data is a good fit to the trend line, or the trend line is a good fit to the data, rather. An r-squared value of 1 means the data is an excellent fit. So here 0.9949 is pretty good. It's a pretty good fit, pretty close to 1. All right, and so now let's use that data to build our model. Our model is the future event. I'm going to stretch this out. So let's build our model down to like September 1st. So I'm going to grab these two columns, the date and the day, the very last one, grab the bottom right hand corner, and that's going to allow me to copy it. Yeah, so let's keep going down. Uh-oh, I went down too far. Yeah, that's 2021, sorry. So if we scroll down to, say, September 1st, so that is going to give us the next few months of data. And then we have to build, we have to model now the number of cases. So this model here assumes it is exponential growth, and this is the equation, and which has the form of y equals ae to the bx, where a is this number here, and b is that little number there. And we could simply type that number in, 1, 2, 2, 3, 3, 6. And we can type that number in, 2, 6. And then we can build our model based on that data. But what I want to do is I want to make this be dynamic, so that every day we have more data to put into our model, so our model is going to become more accurate. And I don't want to have to retype these numbers in every time. So I'm going to use an equation to make that happen. So I'm going to kill those numbers there. And this is more advanced than I would be teaching my own students, but this is kind of interesting stuff. So I just did a Google search for Excel coefficients of a trend line and how to model it. And this is a nice little website here for that very thing. And my students understand slope and the intercept equation, but that's for a linear trend line, but you can also do it for logarithmic or power, or in our case exponential. So this is not terribly complex, but let's just see how these things will work. Okay, so this is where I want to put my my new cases, what I predict is going to happen on the 27th and 28th and 29th of this month. So this is an equation, so we say equals. Oh, sorry, that's not exactly what I want to do. That's, in fact, not at all what I want to do. What I want to do is I want to come over here and write an equation for the coefficients, A and B, for our trend line. Sorry about that. So here, this website calls the coefficient that we're calling A, it calls it C. So this is our equation here. All right, let me see if I can, maybe this is a better way. I just copy that equation, come over here, and I paste it into there. And I'm going to get rid of the Y, because that's my Y data. Okay, so I'm going to get rid of the Y data, and I am then going to highlight the data that is on my y-axis that I want to go into the model, which is the number of cases worldwide. So that's my y data. And then the x data, I'm going to get rid of the letter x, and I'm going to put in the x value, which we see here is the day number. Okay, and then I hit enter. And that number, look at that, is the same as the one from this chart. But it's done dynamically, and because of that, I want to color it a different color. In just a second, I'll do that. And then we'll do the same here for the B term. So the B is equal to this equation. So I get rid of the Y in the same way, and I'll highlight the Y data. Get rid of the X and highlight the X data. And hit enter. And now, lo and behold, it's the same number with even more decimal points. Okay, so we're done with that website, so let's maximize here. And like I said, what I want to do now is all my model data, everything that has to do with the model, I want to color it a different color. It's an equation, but I want it to be different than just a regular equation. So I'm going to color those orange. And now we can build the model with our new coefficients. So this guy here, we're going to follow an exponential growth, so it's going to be this equation here. Equals, and what I could do is I could click that cell, right, times E is the base of the natural log, and it has a function exp in Excel. Okay, and then that number is going to be B, which is this cell, times X, and X in our data is the day number. It's number 7, is in this case number 16. So I can close parentheses, hit enter, and that is the number. I can turn it into a nice little comma if I want to. That is the number that will be on the 27th. The problem is I can't take this and copy it down, because what it's doing is it's using relative references. So for example, this guy here is using this cell and the cell below it, which doesn't have anything in it. And the data here is using these cells, which doesn't have any data in it either. So we can't use relative references, and there are lots of ways to make an absolute reference. I think this is the easiest and the coolest. So let's call this cell, which if you look up here in the name box is H6, let's actually call it A, because that's what we're calling it. We think that this is our coefficient A. So that's easy to do. Click on the cell with the number in it. Not the cell with the letter, but the cell with the number in it. And then highlight the cell box, or the name box, and just type the letter that you want it to be, A. It has to be one word, and not all words are allowed. But A is allowed. And if we do the same for here, B, we highlight H7, and we change it to B. And just to test that, we can say equals A, and that's my number, and this is equal to B, and that's my number. And if these numbers here ever change, then these numbers will automatically change. So let's go down, let's fix our equation. So I'm just going to start from scratch. Equals, again, we're going to use this exponential growth equation, equals A. And now we can just use the letter A, times exp, which is the exponential growth function, onto B, times, and again, our X is our day number. It's the same number, but now look what we can do. We can color it, we can make a little box around it, and now we can drag it down. Okay, so you can see here that these little hash marks simply mean our number is so big it can't fit in the cell, so we have to stretch the cell. And you can see here that on April 1st we reach what, according to the model, again, full disclaimer, this is not typically what's going to happen, although a few days from now it probably will reach 1 million people on or around April the 1st. And so this is kind of exciting to see if our model will predict what's actually happening. Okay, these two data points here continue. This is just the population of the planet, I should say, and this is the percent of the planet that has the coronavirus. All right, so now I can grab all three of those and I can drag them all the way down. this. So the number of cases here has gotten so big that we have to expand the chart. Okay, and then let's take a look at the data. Again, I'm not a biologist, I'm not an epidemiologist, I am a physicist, and this data is just a mathematical model. It shows essentially here's what it's showing. It's showing what will the world look like if we continue with this trend right here. This is only 15 data points, right? And so this is not a great model. We've built our model, and we want to see in the days and the weeks ahead if our model is going to obey, or if the world is going to obey our model, and how effective does our model predict what the world is doing. And so what we want to do is we want to be able to update our model by taking real data as the data comes in days and weeks from now, and we want to be able to get rid of the model and data and put in the actual data. And let's just, we don't know what the future is going to hold, so let's just start typing in, you know, some numbers. So let's just say here, instead of 631,000, that it's 640,000. Let's just make that number up. And instead of 7,222, or yeah, let's just make it be an even 700,000. Okay, and let's just call this maybe 780,000. Okay, so we've just changed that, and so let's just pretend that that is actually our new data. So what we can do is we can, I want to make sure that we uncolor that and make it be white to indicate that that's real data. And again, these guys here in bold, these are not real data points. These are numbers I just made up, but we're pretending that, you know, what happens on the 27th and 28th and 29th of March gets entered at some point. Okay. What we need to do then is we need to then change our graph and also change our coefficients here. That's really simple to do. You may think it's hard, but it's actually quite easy. If you click on a data point on your graph, you can see that we have these two boxes that are highlighted, purple and blue boxes, and this highlights the data that the graph is using. So if you click on the bottom right hand corner, if you get very careful and you look at that little tiny arrow, you can drag it down 3 cells and do the same over here, and then boom, our data then adds those 3 cells. Our coefficients will now change. Our coefficients are close to what they were, but they've changed a tiny bit. This one's gone down a bit, and this one's gone, this one has changed as well. It's gone up a little bit. So we need to also change this data. So if we double click here, we see that we have two different colored boxes here. Again, we drag the bottom right corners, and hit enter, and now that number matches that number, and we do the same here. Drag. Oops, I don't want to do that one. I want to use this one. Come on. Gotta hold your lips just right. And that one. Okay. Hit enter, and now these numbers here, these coefficients that we've just, the equation coefficients should match exactly the coefficients in our graph. That's just confirmation. And so if now our model has changed, and we can now come down here and see what will happen. It's, we see we reached 10 million people before the end of April, which is incredible. And then you could also see, when does 1% of the population get it? 1% of the population, our model tells us, it gets us in the middle of May. 10% is going to be around, you know, the 1st of June. And then 100% of the population will get it at the end of June. So this obviously is again, this is just a mathematical model based on just a few number of data points, but you can see why governments and health officials are kind of freaking out, and this is why the the measures, we use the word draconian. I think it's necessary. The measures for us to quarantine ourselves and to social distance ourselves are necessary because scientists understand exponential growth, and this is what happens with exponential growth. So just take care of yourselves. This data is not meant to scare you. Again, it is just a mathematical model if we continue this trend. And I hope humans are smart enough to realize that scientists understand what they're talking about, and for the governments are trying to not take away rights, but rather trying to save lives. So I hope this was instructive. If nothing else, I hope it was instructive in a use of Excel and mathematical modeling, if not a biological discussion. Anyway, take care out there.